Welcome to Build with Naz. I'm Naz, and in today's video, we're going to do a live coding session where I basically review a lot of details around Rust polymorphism. But before jumping into the specifics of static dispatch, dynamic dispatch, what the impl keyword is, what the din or dyn keyword is, I'd like to take a step back and set the stage for why this is important. So recently I built a crate called Rebel Terminal Async, which allows command line interface programs to be built such that they're interactive and they don't block the main thread, and they support any number of asynchronous Tokyo tasks created, which can also write output concurrently to standard out. So in order to do this, um, uh, there were in order to do this, there were a couple of challenges I faced around making it testable and extensible. And that's where polymorphism comes in. So for example, if you take this Rebel terminal async crate as an example, it takes as input essentially something in the operating system that relays user input events as a stream to this program, to this Rust library. Also, it needs a way to output or emit display, in this case, ANSI 256 escape sequences, encoded strings, to standard out or standard error, but not directly to standard error or standard out because it needs to be buffered. That's how concurrent output to these to standard out or standard error would be supported. So in order to do that, let me actually show you the real code here. So if you look at this is the Rebel terminal async crate source code, and one of the actually here's the let me show this. Yeah, here we go. So it's in here, terminal async, and so essentially one of the first things. One of the main things that this, in order to use this, one of the main entry points into the crate is this readline struct, and this is the thing that essentially generates a prompt and allows user input events to be accumulated and also essentially output. It provides a way to generate output so that if you have any tasks that need to do like print line, then essentially this struct does a whole bunch of setup to make that happen. And where polymorphism comes into play is that originally when I had written this crate, like in the early days, because I have videos recording that journey, this wasn't this thing that you see here, which is din, write, and send, which is, what the heck is that? And this wasn't, it was just standard out or standard error. You would just pass in standard out or standard error. And this wasn't this pin box din stream which takes a result, which contains an event. It wasn't this either. So that was just a cross-term, I think, event stream. So those are great to get started, but in order to test it, they were essentially dead ends because there wasn't really a way to test it because I couldn't, because the standard in is standard in. It comes out of the standard library, and event stream isn't something that I could modify. So essentially, if you look at the code today, and I'll post links to this in the video description. Essentially, there's something called a, let's see here. Let me open this up. I have a way to mock an input stream, and if you remember the pinned input stream, that din stream thing, that's used here in tests, and also I have a struct that essentially behaves like standard out or standard error, but isn't actually standard out or standard error. It's just a buffer, and the reason it works is that the if you look at the the type that readline receives, it's one of these din, write, and send things. So this is kind of like jumping to the end. I wanted to show some real examples of polymorphism in action. But before we get into those examples, I have like 2 or 3 different crates I want to show. I wanted to get into the actual nitty-gritty of Rust polymorphism. Like if my background is, I used to work at Google. I've worked in JavaScript, TypeScript, Java, Kotlin, a whole host of other languages, and I was very familiar with object-oriented programming. And then when I came into Rust, the functional nature of it was one of the things that I had to get my head around. That was one of the major sort of mental models that I had to grok before Rust made a whole bunch of sense. And beyond that, polymorphism is something that was a little bit more complicated of a topic to kind of grok for me as I started on my journey. And and so essentially, like one of the um, uh, one of the things in the type system is that Rust is very explicit, and it makes it such that concrete types have to be explicitly declared, defined. So when you have to declare them, and then when you use them, you have to, sorry, you have to define them explicitly, and then when you use them, you have to declare them, and which is nice when you're going after a specific type. The compiler can provide all kinds of niceties for static analysis. The only downside is that if you wanted to write code like this one, where you want to be purposefully vague about what this new method, this new function receives as a second argument and what it receives as a third argument, if you want to be vague about this, then things get a little bit complicated complicated relative to how straightforward it is to use concrete types. And so in Rust, polymorphism happens in 2 different ways. One is through generics and something called monomorphization. And that means that's essentially at compile time, the static invocation of basically, essentially, you can think of polymorphism in Rust falling into 2 different camps: static and dynamic. Dynamic is something that's resolved at runtime, and static is something that's resolved at compile time. And so at compile time, we have generics and monomorphization, and at runtime, we have this din keyword, or something called trait objects, which is essentially where this din keywords comes into play. And the crux of it boils down to Sizedness. So essentially, in Rust, if I have a concrete type, then the compiler is able to deduce the size of it. And so this is necessary for the compiler to figure out how big of a thing it is that it needs to put on the stack, or what the size of something is when it passes it as an argument to a function. Or when you return something from a function, it needs to know how big it is in order to be able to size things correctly. And so sizedness is a thing that almost every struct in Rust that you create, or most of the structs that come out of the box in the standard library or anything in Rust, really, they're all sized. So there's this really nice article you can get into of sizedness. So when we talk about like static or static dispatch, which is something that's determined at compile time, essentially the compiler deduces using generics. It essentially, like when you have a type that's generic over a bunch of other types, then the compiler ends up generating concrete code for each and every one of those permutations and combinations. And so that can end up increasing the size of your compiled binary or library. On the flip side, when dynamic dispatch is used using trait objects, there's this thing called a vtable that is used to look up information about what functions or methods are available on a particular trait. So those are actually 2 very different paths. So when you go down the path of dynamic dispatch, it leads to type erasure because you end up referencing a variable not by its concrete type, but by a pointer to a trait, and by its very nature, a pointer to a trait isn't sized because a trait doesn't have a size. A struct has a size, and so if many different structs implement the same trait, then what is the size of the trait? And thus the compiler doesn't know. And that's where you see things like din. You'll see this all the time, like with din error. You've probably seen like box din error, and you're like, what is going on there? So in order to get an answer to that, this is a really good read about how sizedness ends up having an impact on what dynamic dispatch ends up looking like, and also how static dispatch looks like. So in order to get a handle on all of this, oh, by the way, when you do dynamic dispatch, and I'll go into this in a little bit more detail in this later on in the video, but there is this thing called a vtable, and it essentially is a lookup table that at runtime, Rust essentially figures out at runtime when a particular method is called on a variable which is of type the trait pointer to the trait. Then there's a lookup table called the vtable, which is used at runtime. And there's some really, really, really good videos on this. Like, I definitely recommend reading this or watching the Crust of Rust dispatch and fat pointers. This goes into a tremendous amount of detail into all of this. For Sizedness, this is a fantastic article. I'll put links to this in the description. And also there's some other videos that I found that are really good, which are worth taking a look at, and I'll share all of these actually. But in order to get started, let us actually create a project so that we can get a sense of like what the different flavors of this kind of polymorphism looks like. And the two camps are static dispatch and dynamic dispatch. And so let's explore static dispatch first. So let us do this. Let's make a new crate called dynamic dispatch. And let us open it here, dynamic dispatch. Okay, let me move this to the correct place, and let me increase the zoom level. Oops, what happened there? Zoom in. There we go. Okay, so yeah, should have made it a library crate, but that's okay. So let's do this. In order to get started, let's take the example today of the error trait. So what we want to do is, using the error trait, explore how dynamic dispatch and static dispatch can be used to work with errors. Errors meaning that different structs which implement the error trait, and what that might look like, how it feels when we go down the static dispatch route and when we go down the dynamic dispatch route. So before we begin, let us create our first error, and we're going to call it error 1. And let's see what we're going to do. And by the way, we're just stuffing out the we're going to end up using we're going to build two structs, each of which implement the error trait. And let's see, what is the error? Oh, right, so we need a main function. Actually, why don't we just call this librs? We don't want, this is going to be a library crate. Okay. So here we're going to do, let's say, we're just going to make a struct called error1, and we're going to, let's see, let's derive debug for it. And then in order to implement error, so we're going to implement error for error1, and let's see, let's import error. Let's put this up there. Actually, let's also do, let's see. Oh, we don't need to implement default. So the reason it's red is that, oops, let's look at the error message. So essentially, the error trait has it has trait bounds, and that means that anything that implements the error trait must also implement debug and display. So that's why we did debug, but we haven't done display. So let's do. Actually, I mean, we could actually done an explicit implementation of debug, but derive is fine because we're not actually going to do anything with these implementations. It's more. So let's oh, actually, that's right. So implement. That's exactly right. So here we are implementing the display trait and debug trait for this struct, and so now we have one error. So let's do error 2, and that's essentially the same thing. Like this is just to stub out that okay, we have 2 different errors, and then let's do this because I don't want to have to import it in the rest of the file. And okay, so now we have 2 errors. These are concrete structs. They have a size, and they are 2 distinct types. Both of them implement the error trait. So that's all we have so far. So so one thing we might want to do next is that when we explore static dispatch, we want to be able to choose between either of these types at random. So just to kind of set up the rest of the examples, let's set up a random Boolean generator. And for this, I need to add the rand crate. And so, because then that'll give us the ability. So it's public, so random, and yep, that's it. Okay. So there's our random Boolean generator. I mean, we could have just used this, but this is slightly easier to read. And then, okay, so now let's explore. We're going to actually explore static dispatch first, and we're going to explore static dispatch through 2 lenses. One is receiving errors in a vague or generic way, and then returning errors in a vague or generic way. I shouldn't say generic. In a using the trait rather than using the concrete struct. So so here we do, let's see, let's have, actually these don't need to be pub. I don't know why I made them pub, because they're just in the context of this particular file. So then, okay, so let's do this. So for static dispatch, we will have, so we need to make 2 different examples. One is receives, and the other one is returns, because this will be a nice way to see how they differ. So returns, and then for the receive, the thinking here is that we want to make a function that receives a trait object rather than a concrete error 1 or error 2 struct. So naively, we can just say, you know, fn handle error, and then we could say error, and then we could say, you know, error 1. I mean, we all know how to do that. And then, but then how would we take error 2 as an argument? Would we make another function called handle? And we can't, because they collide. Because in Rust you can't do that. It's not Java. So so what do? Well, what we have to do is we have to tell the compiler that the argument that we're receiving, that its type cannot be the concrete type error 1 or error 2, but something that is similar. So in our case, what we want to do is it's a type T. We can call it E. That might be a little bit easier to read. And this one will be, and so basically we set a trait bound. This is the where clause, where what we're saying is that there's this generic E, which the trait bound on it is the error trait, and we can receive that as an argument. So as long as the compiler gets something that matches the signature, it'll work. And we know that this works because the debug trait is implemented. And if we did something like this, handling error 1, this is debug, and this is display, this will also work because this trait bound ensures that we have debug and display. So there's an example of receiving a this takes ownership. We could have put an ampersand in there if we just wanted to borrow it, but this is a simplistic example where I'm like, okay, cool. If you say it this way, then this happens. So the thing to note here is that we're using generics. So this is not dynamic dispatch. This is static dispatch. That means that the compiler can infer all of the stuff at compile time and replace all of our code with actual concrete types. So it'll actually generate and handle error for error 1 and then also 1 for error 2. So if you look at the compiled output, you'll see 2 different variants of the handle error function. And so, which is great. And so basically what this is just syntactic sugar for let's see, let me show you this. So this is, so let's say we didn't want to be so verbose and we wanted to use some syntactic sugar. What we could do, let's rename this, we say accept error, and then let's do accept another variant of the same thing, but this time we're going to say with syntactic sugar. And here, very nice, Copilot. There it is, the impl keyword. So whenever you see impl being used as a receiver in a function or in a return type from a function, it just desugars into vaguely, I mean, you can think of it this way, desugars into something like this. So you can either write it this way or you can write it that way. They end up being static dispatch. So let's say that we wanted to actually make a function which let's say, let's see, we have returns. So let's say we want to make a function which returns a single error, right? So return a single error. And so check this out. This does not work. So let's do a variant of this. So we can say pubfn return error 1. So that works. So why does, or let's try this. We can say pubfn return error 2. That works as well. How come this doesn't work? Let's look at it a little bit deeper. Okay, so let's see what the error message is. If and else have incompatible types, expected error 1 found error 2. Oh, interesting. If you change the return type to expect trait objects, let's look at here. So the compiler actually tells us how to resolve this, and it's saying, you know what, stop using static dispatch. In this case, you got to use dynamic dispatch, and then you have to use the din keyword or the dyn keyword. I'm not really sure which way to pronounce it. I've heard it said both ways. So with the din keyword, when you return something, you generally have to box it, or you can wrap it in an arc. I will share more information about when it's appropriate to do one or the other, but that's the next section we're about to enter. So to kind of like simplify what the compiler is saying, it's saying that impl error at compile time will be resolved into a single concrete type, and there are two different concrete types that might be returned from this if statement. And so the compiler is like, I don't know which one to return, and so the error is out, which is fantastic. That is exactly what we expect. So so let's see if we can do a different variant of this where we're like, well, okay, what if we do something like, let's see, return single error, and now we want to return concrete, let's say, type where the type is error, right? Let's see, will this work? Okay, so this signature seems okay. Let's try this, error1. So this doesn't work either. So the caller chooses a type for E, which can be different from error1. So let's see, so we can do, oh right, so we can do impl E. So that works. So this is, oh no, that didn't work. T, still didn't work. Okay, so what it's saying here is that you can only do an impl of a trait, and so we could say error, and get rid of this. And so that essentially is the same as this. So we basically boil it down to that, and so that works, but that other syntax where we did, you know, the unfolding the syntactic sugar, this approach, that it doesn't like so much when it comes to return. So, but that's okay. So essentially, there we go. So for this, for static dispatch, where everything is determined at compile time, all the things are sized. The TLDR is that when you receive something in a function, it has to be sized, and even if you're using generics with trait bounds, the compiler will ultimately generate code that has no generics in it. It's going to be specifically tied to concrete types, and the compiler will generate essentially multiple variants of this function. One for let's say error1, and one for error2, one for error1. And so that's the static dispatch. It's done at compile time. It's all static. There is no din keyword. There's no box. So now let's look at how to implement this, because this fails, right? This does not work. Need dynamic dispatch. And the reason we need dynamic dispatch here is because what we're saying is that, okay, I want to return a thing that implements the trait. And the thing that implements the trait, it can be error1 or error2. These are two completely different types. And so the only thing that's common between the two of them is that they implement the error trait, which we did at the start. So here, implement error, implement error. And the way we can express that in Rust is using the din keyword. So, and the rule of thumb is that if you receive it, you can take a pointer, a reference to something that's some din trait, and when you return something, then you have to box it, either box it or arc it, and there are pluses and minuses. So if you box it, and we'll get into this just now, but if you box it, a box essentially takes ownership of whatever type you give it, puts it on the heap, and it gives you a pointer to it. That's that pointer indirection is what we're leveraging in order to be able to get around the fact that we don't know what the size of the type is, because the T in box T is a trait, and the trait doesn't have a size, because the trait might be implemented by one struct which has a certain size and a different struct which has a different size, so we cannot make any assumptions. So what we do is we use pointer indirection, and instead of pointing to the thing, instead of knowing the size of the thing, we say that we know the size of the pointer, and we know that the pointer points to the thing. So that's how we get around knowing the size of the thing. We have a pointer that points to the thing, and that's called a fat pointer. And you can read all about it here, but essentially the two ways you can do this is you box it or you arc it. And if you don't need shared ownership, box it. If you need shared ownership, then arc it. If you need shared ownership just for read access, you don't need to put a mutex. You don't have to wrap T in a mutex. But if you need interior immutability of this arc, then you need an arc mutex t. So that's the gist of it. So coming back to dynamic dispatch, we're going to do a very similar kind of thing where we say dynamic dispatch. Oh, what is this? Control right arrow. Oh, I'm doing control right arrow. Whatever. So let's see, dispatch, then we say use super, and okay. So in here we have two modules, which is, let's do the receives, and it actually filled out the code. Wow, that's pretty good. So let's do this. Let's comment this up for now, and let's do, actually, no, that's fine. Let's do this. Okay. So basically, this is one variant of receiving receiving an error. You can do it by ref. And so basically, the ampersand is a reference, which is a pointer, and so this has a size. So the compiler knows what the size of the pointer is, and that pointer points specifically to error. So the thing that you pass to this might implement other traits, but for the purposes of this function, it will use a vtable. Where is this vtable? This thing. To look up just the methods for the error trait for this struct, or whichever one, error 1 or error 2. So essentially, I can now pass in a reference to error 1 or error 2, and I can use it. So for example, I can say pubfn, whatever example. One is, we can do, we can say something like error 1 equals error 1, and look, we can do that, and we can say let error 2 equals error 2, and that works. That's wonderful. So, and the reason it works is because we didn't have to box anything, we didn't have to arc anything, because the reference, the ampersand, is a pointer. So it's a smart pointer. So we can do, actually the box is a smart pointer. This is just a reference. Anyway, but so we can do another variant of this where we say pub fn accept, actually it should be receive, not accept. Receive error. Okay, so we can say pub fn receive error by box. That's exactly what I was thinking. So basically, another way is that when we don't want to use a reference, we can just say box. And you can imagine you can replace it with arc and it would achieve the same outcome. So if we want to do pub fn example2, we have, there you go. So essentially what's happened is that create a new error1 variable. That's a struct. Then this is allocated on the heap at this point. Then this gets moved into the box. Now it's in the, I'm sorry, this is allocated on the stack. Then this gets moved into the box. The box is in the heap. And then what we have here is the, let's see. Actually, let's see, let it equals, yeah, this one. So here we have a pointer that's on the stack, which is pointing to some space in the heap. We know that the size, what the size of this is. We don't know what the size of that is from, I mean, we do know in this case, but when we go to call this function, all that information is erased. So that's type erasure. So basically from, if you go inside of this function has no clue that this is error 1 or error 2. So that's basically what's going on there. So that is the receiver. So now let's look at mod. Let's see. So now let's say we want to do returns. So let's say that, actually before we do, actually before we get into this, let's do one more where another use case for trait objects is that what if you want to receive a slice of things, and those things are different concrete types. So for example, you can't make an array with more than one type, concrete type, but you can make an array or a slice with which basically is of type pointer to din trait, because the pointer to din trait is sized, and so that size is the same in that array. So let's just give an example. So let's say this is, let's see, we want to do receive. Can never spell receive. Let's see, receive slice of errors, and what we want here is, let's see, what we want is a slice which is, so you would think, actually you would think, let's see, it's a slice of error. Okay, so, and then we can say for error in arg. Yeah, okay. So, wait, I told you this would work, and it's not working. So what's going on here? It's saying that the size of the values for din error cannot be known at compilation time because it's not sized. Okay, and slice and array elements must be sized. What it's saying is that this does not have a size, which is correct, but this does. And there you go. That's how you fix that. So now we can pass a array of these things as references, which is pretty cool. So that's how you can do that, and you can also do like blocks of this. That'll work too. So let's see. So now this is pretty cool. Receiving a slice of errors, and then so now let's say we want to return something. So let's say, and this is basically to solve this problem. We want to return a random error, so we can say pub and return one of two errors, and that is correct. Look at that. Essentially, what we do is, depending on the random boolean, if it's true or false, we box up one of these structs or one of those structs. Pretty straightforward. Then we have return one of two errors and two errors with arc. And remember I said we could use arc. There you go. There's arc. And then we can do something like, what if, okay, so this is great. We're returning an error that we've constructed here, but what if we wanted to return multiple errors? So let's say pubfn return slice of errors. So this is not going to work. This code that it gave us is incorrect. So what we will do is, instead of vec of this, what we need is a vec of din error. Okay, so that's not going to work. We need a, because this is not sized. And so actually let's do this. Instead of box new, let's do, oops, let's push references. That's not going to work either. So let's do this. What we want is a vec of those things, and what it's saying is that that won't work because what we need to do is essentially we're returning something from like we're returning something that was made inside the function, outside the function. So what we're now saying is that, hey, don't drop it. So here also we need some more clarity around what exactly we are returning. So this is din error, and there you go. That's what we need to make the compiler happy. So if you drop this, it will complain because we're returning something that was allocated here. But if we make it static, that's fine. And by the way, if you may have a function that returns a string slice, you can do the same thing like this. And so that's one way to return. And we can also, let's say we want to mutate. Let's say we want to receive a mutable vec of these things. not a slice, but a mutable vec, what would that look like? So let's do mutable vec containing different types of errors. And what we want to do is, let's see, we want to return nothing because this is, but we do need to receive something. So what will that look like? So let's do immutable vector, and here it's going to be not din error, it's going to be din error. So what we can do is that we'll need to introduce some lifetimes in a minute, but let's do this. So let's say, so we receive a mutable vec, and what we can do is mutable vec, no, we don't need to box it. We could, because this works. This will also work. This one. Oh, no. Let's see, we got to choose one or the other. Oh, wait, what? Mutable vec of box of, no. Mutable vec of this. There we go. There we go. So what we're saying here is that, okay, I'm going to give you a mutable vec. You accept that, receive that as an argument, and then you can push this concrete type or that concrete type, not directly, but you can push the reference to that concrete type or this other concrete type. And then, so that's how that works. And so there you go. Those are all the sort of different ways in which you can play with like dynamic dispatch versus static dispatch. And yeah, so that covers the sort of intro to like the static dispatch, dynamic dispatch, and then next I want to jump into like how this is actually used in practice, because this is really good, but it's also very sort of rudimentary. And let's look at how this is actually used in the real world, so to speak. So looking at this readline Rebel terminal async crate and the readline struct inside of it, we have an argument called safe raw terminal. And if we look at safe raw terminal, so remember whenever you see a din trait and then some other trait bound, is an auto trait, you know that you're going to have to probably box it or arc it. And if you want interior immutability, you're going to use arc mutex and then this thing. So that's kind of like what you're seeing here. So here we have the din write plus send, the auto trait. This is so that it's thread safe. It can be sent across multiple threads. And so what we have here is an expression which says something like, okay, you can pass standard out here, or you can pass standard in, and it will just work. You have to wrap the standard in and standard out in an arc mutex. STD mutex is just a alias for this. So both standard in and standard out implement the write trait. I'm sorry, standard out and standard error implement the write trait, not standard in. Standard in does not. So this is a way to specify in a vague or polymorphic way. You can pass in arc mutex standard out, arc mutex standard error, or arc mutex safe writer or shared writer. So shared writer is this thing that allows Tokyo tasks to generate essentially output that will be dumped into standard in, standard error or standard out, whatever this is. But it'll happen in a asynchronous manner. So when one of these is created, it returns itself and it returns a shared writer. So I won't get into the details of what shared writer is, but shared writer itself, look at that. The write trait is implemented for shared writer. So essentially, if you look at standard in, standard out, shared writer, they all implement the write trait. And I have an additional bound for send because it's wrapped in an arc mutex. So that's roughly how this shows up in practice. Let's quickly jump to a test for this, and then I'll come back to the third argument, this one. So for the test for this, if I go all the way down to this file, and I'll provide links to all of this. This is all on GitHub. Let's see, and this is a published crate as well. So if you look at standard out mock, that's a thing that I can use to test readline without actually instantiating, without actually using standard out or standard error. Because look at that, standard out is a struct, and I have an implementation of the write trait for it. So that's how this kind of works. So ultimately, standard out mock, standard out, standard error, and shared writer all implement the write trait. And din write plus send, they all actually implement that, believe it or not. And so that's how this polymorphism works in practice. And so I am able to, without actually using a real standard error or a real standard out, I am able to test the functionality of this crate. So if you look at this test right here, what it does is that this is test read line something, something, something. Essentially, it goes, all right, let's make an output buffer, and we're going to pass that output buffer into the standard out mock. Since the standard out mock struct implements the write trait, we can write to it. And when it writes, instead of going to standard out or standard error or to a shared writer, it'll actually end up in this buffer. And then we can test that to see if what we expected worked or not. So this basically creates a new read line with this standard out mock thing. And let's see, what it does is that, let's see. Oh, and by the way, you can clone it because it's just an arc, so arcs are cheap to clone. So when you clone it, you're still getting that same buffer. So because it's used later on, I'm assuming in other places in the code. Yeah, right there. So what we're doing here is that, actually, I didn't have to clone it. I could have just used standard out mock, drop the clone, and I could have just tested the output buffer. But that's okay. Because we still have access to, oh no, it's moved. You know what? Never mind. This test is correct. Because we move output buffer, actually, this gets moved in here. So never mind. This is correct. So yeah, we construct a new read line. We pass in the standard out mock to this thing, clone it and all that, and then let's see, we do a bunch of stuff. This is actually typing A, and we'll talk about how A got typed without using a keyboard or interfering with the operating system. How did this work? Well, this is literally the next thing on the list. And essentially it does a bunch of assertions, and it looks inside of the buffer of this thing, and it goes, oh, okay, you have whatever, the prompt followed by A. That's roughly how you read this test. So that's cool. That works. And so that's why using polymorphism with a trait object, I was able to write a test for that. So let's look at the other thing that this new function takes as an argument, which is a pinned input stream. What the heck is this? So okay, so an input, these are async input streams, and so cross term. Let's see, where is cross term? docs.rs cross term. Let's look at what the heck just happened. Docs.rs cross term. I don't know what that was. And let's look at event stream. There we go. So this event stream thing is an asynchronous input stream. And yeah, so you can look at the Tokyo docs actually. Do I have them open here? Yes, right there. So check this out. They have a lot of good stuff. There's async streams in here as well. And so this is basically an async stream that implements async read and async write. So we will leverage that fact in a moment. But for now, what we're saying is that, okay, it's a thing that implements stream. Stream is this asynchronous stream from futures, the futures crate, and it can yield items. And the item in this case is a result of type event. And if it's not an OK variant, then this is the concrete. Look at that error. So it can return an error, or it can return a cross-term event. So that's what this is. And it's pinned because async streams for asynchronous reasons need to be pinned and boxed. So let's see. I have a separate video, I think, on that, or I'd mentioned it in a different video. I might actually do a whole other video on async and dive into that in more detail. But for now, let's just skim over that because that is not the purpose of this particular video. So here, pinned input stream. Let's look at what concrete implementations I have of this thing. So if we look at so one thing that implements pinned input stream is event stream, this thing. Believe it or not. So when we look at how it is used, an event stream, this event stream, the cross-term one, simply gets instantiated. It gets pinned and boxed, and voila, that's the argument that this takes. So that's the real one. So this is like, by the way, like dependency injection in action, and so this polymorphism is another way to implement dependency injection in Rust. So let's look at in a test environment or test context what this looks like. So here I have a made up pinned input stream, and there's a stream macro. Again, it comes from the async stream crate. And this one, there's Tokyo docs on this. It's all in here. Async streams, this one. So you can read through that and get a sense of it. But async stream. So there's that stream macro that I'm using here. So essentially what that does is that, let me go back to unit testing here. Okay, so what it does is that it goes, okay, in this vec, which has some hard-coded events, like what cross-term would report if you had actually typed A, B, C, and enter. So I've hard-coded those events. And I said that, okay, put them in a vec and serve them up as a stream, pin and box the thing and return it. So this is used in tests, which is pretty cool. You can just see, like, that's how rudiment, like, kind of, this is roughly what it works. You can just, like, iterate this input stream and get things out of it, which is not very useful. But where it is useful is that same example we were looking at. So here I had created readline, and you remember we had a stdout mock, which is great, and now we have a input stream mock, basically. And what this allows us to do is essentially we can basically let's see, let me give you a different example of let's see, test readline. Maybe let's see, what does this do? Yeah, so here we have ABC enter. So basically, this one creates a readline with the stdout mock and the made-up input stream, which types ABC enter, and it goes, hey, make me a readline, and then call readline await, and that should basically, when it gets a ABC and then enter, it'll return ABC, and so it gets a readline event. So basically, it goes, okay, your read line event, the variant is line, excellent. And it should contain ABC and not enter, because we typed ABC, enter gets dropped, and that's what the read line event says. So this is how we've mocked you can think of it as the keyboard and the mouse or any kind of input into the process. We've mocked it using using this async stream, and all that was possible because of the polymorphism with the trait objects that we're using here. So that's a real world example of how to use this. And wanted to show you one more example here. This is in a different crate. This is a TCP API server. It's just some TCP API sort of backend that I'm still. It's very experimental. I haven't put it in any official Rebel open core repos or anything, but this one has some really cool examples actually of this polymorphism using the dynamic dispatch. So let me walk you through a couple of them. So what this project is that it's this thing. Let me make this font bigger. Okay, so here we have. So I'm going to run the server. So there it is, TCP API server. I'm going to run the client, and then essentially I can send commands. This actually uses Rebel terminal async under the hood, and so I can say, and it has a key value storage in the back end and all that. But I can say things like get all, and that essentially sends a message to the server, gets a response, and I can say exit, and that's basically what it does. So essentially there's and also I can do things like that. I can start the server, start the client, then I can kill the server, and the client also drops. So that's what this TCP API server thing is. And I want to write a test for the server. So the server is it's binary basically. There's like a main RS, and depending on what command line arguments you pass in, it spawns the server or the client. So this server underscore task RS, there's server underscore main is the main function that that handles opening let's walk through what it does. So it gets the address on the port. It starts a server by binding to that port. Then, oops, this one is not necessary. Then it sets up a cancellation token. This is so that there's a whole bunch of tasks that get started so they can all be gracefully exited cooperatively. And then what it does is that in a Tokyo select block in an infinite loop, it checks for cancellation. That's one path. Another path is that it's erasing these two futures. This future and that future are being erased. So then what it does is it gets the TCP listener, it accepts the incoming connection, and then it spawns this thing. It spawns, let's see, it spawns this function. So we have that. So for incoming connections, this function handles the, like when you say to start the server and then you start a client and you say get all, that's what this is, this event loop thing. And let us look at the test. How do you test something like this? And so I was like, okay, I wanted to mock essentially the TCP stream, because if you look at this this function that does the actual work, it receives a TCP stream from this thing, and it gets a TCP stream from the listener.accept, which is when it accepts an incoming connection, it gets a TCP stream. It passes this TCP stream to this function, which actually then deals with it. It does a bunch of stuff that the server is supposed to do. So I wanted to test this without actually spawning the server. And so one thing that I did was that, okay, notice, let's see, TCP stream. Okay, so this under the hood turns around and uses it gets a buffered reader and a buffered writer to read and write from the socket, and it uses this thing called byte IO read and write. And this is where we get into the trade objects. So notice that let's see, we are getting a buff reader to an own read half, which comes out of a TCP stream. These are concrete types. Well, maybe they're not. I'm not really sure. We have to look at the Tokyo docs to figure it out. But is it? Yes, these are concrete types. So, so here, what I'm doing in this byte IO, which is actually the module that takes care of reading and writing from the socket, I pass the buff writer or reader to this byte IO module, the reader write function. But if you look at the, let's say a real example. So look at write, we're passing in buff writer, own writer half. But look at that. That's not what this says. This says buff writer, where the writer, it's just a made up trait. And the writer is basically async write plus unpin. So essentially, this is, let's see. This is not a trait object. This is using generics. So here we have basically the compiler figuring it out at compile time that, oh, okay, I can essentially it's a static dispatch pattern, but for polymorphism. So this also works. So which is pretty cool because there's no din, there's no box, there's no arc. It's just a mutable reference to something that's and this is generics. So here it's basically impl async write plus unpin. And so here I am able to pass something that's a the one half of a socket, the reader half or the writer half. Let's see how that's a writer half. The reader half, I think, looks similar. Yeah, similar. So buff reader, where reader is async and unpin, so it implements async and unpin. Again, not dynamic dispatch, static dispatch. So that's pretty cool. So essentially, the reason it doesn't say like buff writer owned read half or buff writer owned write half is because I wanted to be able to mock this. So if we look down at the test, I have a way to mock a TCP stream. So I just mocked one half of it because I'm still working on it. But essentially, there's a struct called mock TCP stream write. So this is the right half of the TCP connection that we're or TCP stream that we're actually mocking. In order for this to work, let me show you the protocol. Yeah, so write takes a thing that's async write and unpin. So here I made a, where is it? Mock TCP stream write. Actually, got this new extension that, let's see if it works. Yes, it does. It basically collapses everything above and below the code block that I'm trying to show. I should use this more. Let's see. So we have, okay, mock TCP stream write, and that implements async write. And if we look at this one, we have, let's do the same thing. Oops. There we go. So here we have like, get this out of the way. Here we go. So we have a mock TCP stream write. This is the right half of the TCP stream that I'm mocking. And all I have to do to mock it is, because remember the type of the thing that this function receives is a buff writer of a thing that implements async write and unpin, and it just so happens that this thing implements async writer. And if we expand this out, you can see there's the implementation of async write. There's a poll write, poll flush, and poll shutdown, and it's just made up. Basically, when something writes to it, it just takes whatever is written to it and dumps it into a buffer. And because it dumps it into this vec of U8s, we can then test it to see, let's undo this thing that I did. And let's see what the test for this looks like. So let's see. Here's the test. So let's do this. Okay. Wow, this is a very cool extension. I think it's called, what is it called? Fold or something? I think it's called Better Folding. Yeah, this thing is awesome. That's what I'm doing, Zen folding. Okay, so here we have, I'm testing just the right half of that code, the server logic. And what I'm doing is like setting up a whole bunch of like fixtures to make that function work, and then I go ahead and I basically this is the function handle client message, and let's see what it does. So what's happening here is that I make my mock TCP stream write. This is the right half. I wrap it in a buff writer. I actually put a bunch of things in the buff writer. It's a protocol for this server. It's something called length prefix. So basically, it figures out the payload of the thing it's supposed to be sent over the socket, and then it writes the length of it, but as a fixed number of bytes. So hence U64 or write U64. And then what it does is that it calls this handle client message. That's the function up there that I am actually mocking. Not mocking, sorry, testing. And look at that. It passes the buff writer to it. The punchline, there it is. So then, let's see. And then, let's see. It gets the bytes in the buff writer. And I forgot to do an assertion, didn't I? Okay, I'll put that in later. But yeah, essentially there's an assert missing. So when you run this, it actually looks like that. So it kind of like dumps all the bytes that it's expecting, but what's supposed to happen is there's a payload bytes. It needs to do an assertion to make sure that the thing that got sent over the socket is what was supposed to be written. So I need to add the test for this here. So this is a oops, I'll do this after the video recording. Okay, so but yeah, I mean, but you could see from the print line that the actual bytes, these are the things that are actually sent over the wire, and all of this zeros and all these numbers are basically a vec of U8s, and it actually works. I just didn't. I dropped this. I think I had it in there, but I don't know where it went. So there you go. That is an example of mocking a TCP stream, the right end of it, half of it, and then using static dispatch in this case, not dynamic dispatch. And oops. And then in this other case, we ended up using dynamic dispatch. So they're both available. You can use whichever one makes sense for your use cases. So I will put a link in, a lot of links in this video, and I'll also do a blog post write-up of all the information in here because there's a lot. So yeah, I'll post all that as soon as it's done. Also, if you like the style of this video, please give me a thumbs up. If you like this kind of content, please subscribe to the channel, turn on your notifications, because then you'll be notified when new videos are dropped. And also check out developerlife.com. You can subscribe for updates, and so that way you have a way to know when the blog content is updated. Thank you so much for watching, and I will see you in the next one. Have a great day.